Okay, hi everyone. Thanks for joining us on this live stream again. We are going to be doing a Q&A about computer science related to the physics project. I might just mention that tomorrow we'll be doing two things. First thing, we'll be doing something I'm itching to get going on, which is to actually start doing some working sessions, figuring out some science, which we'll be live streaming. And the first topic we'll be talking about is trying to understand quantum spin and electric charge. And that will be at 2:30 Eastern Time. And then at 4 o'clock Eastern Time, I'm going to do a talk about our project and what we're doing for kids. Okay, well, let's get started. We want to talk about computer science. Probably it'll be a mixture of theoretical computer science and more practical computational questions. So where are we going to start here? If we don't have a question, I'm going to start asking questions here. Do we have something? Maybe we should talk a little bit about quantum computing and about the different. I think we had some questions yesterday that we punted on because we were talking about physics and math kinds of issues. But maybe we can start off talking about, okay, so the question here, can we simulate quantum computers using multi-way graphs? So I think we should talk a little bit about the relationship between NP computations, non-deterministic computation, multi-way graphs, quantum computation, and so on. I think that would be a useful place to start. And maybe Jonathan would like to say some things about that. And I want to say, by the way, that this is intended to be a somewhat technical Q&A, so we're not going to necessarily explain all terms that come up. Encourage you to look them up on the web or whatever if you're not familiar with them. If you are, just jump right in. So anyway, we're talking about non-deterministic computation versus multi-way graphs versus quantum computation. So Jonathan, do you want to describe what we think we understand about that?
Sure. So I can briefly sort of recap some of the things we mentioned yesterday about this topic, and then hopefully people can ask more in-depth questions later. So one of the really nice features of the multi-way evolution graph, from my standpoint, is that it provides a very clean intuition for the differences between all of these different modes of computation. So if you have a classical Turing machine that's completely deterministic, has a completely deterministic transition function, and so from the point of view of a multi-way system, if you think of every multi-way branch as performing a computation, a classical Turing machine is therefore following kind of one particular multi-way branch according to a purely deterministic rule. A non-deterministic Turing machine, which rather than having a transition function has this partial transition relation and therefore has non-deterministic behavior, you can think of that as corresponding to, again, a single path in the multi-way system, but where that path is chosen in accordance with a non-deterministic rule. Finally, for a quantum Turing machine, there's this notion of a transition monoid, where your space of states is replaced with this Hilbert space of quantum states, and your transition function is replaced with a transition monoid. And again, from the point of view of a multi-way system, you can think of that as basically corresponding to the entire multi-way evolution graph. So the multi-way evolution graph, all of its branches, you can think of as each branch is evolving a separate eigenstate of some quantum system. And so the overall evolution of the multi-way system is like an evolution of a linear superposition of those eigenstates. And that gives you, I think, quite a nice intuition about the distinction between classical Turing computation, non-deterministic Turing computation, and sort of quantum computation. Maybe, I don't know, do you think it's worth talking a bit about sort of non-deterministic versus deterministic complexity classes, or should we?
Yeah, let's talk about that. And let's talk about also what it means for, the big question is, how do quantum computers, what can we say about quantum computers and their ability to solve NP-complete problems? And,
okay.
I think that would be a good topic.
Right. Okay, sure. Well, actually, let's start by saying something about the nature of NP-complete problems with respect to these systems. So again, one of the things I think is really nice about this is that if our sort of interpretation of this computability theoretic or computation complexity theoretic interpretation of multi-way evolution is correct, it gives us a really nice intuition about things like the P versus NP problem. Because, okay, so for instance, the one standard way of formulating the P versus NP problem is you're basically asking the question, is the set of problems that can be solved in polynomial time with a classical deterministic Turing machine the same, identical to the set of problems that can be solved in polynomial time with a non-deterministic Turing machine? Well, if what I just said about the multi-way system is correct, then that has an immediate kind of intuitive formulation in terms of multi-way branching. Basically, what it's saying is, if you can reach, if there was some state in the multi-way system that you could have reached by a path chosen by a deterministic rule, could you also have reached that state by a path of approximately the same length, or with the sort of the same scaling law, but by following a path that was completely non-deterministically chosen? So obviously, the fact that those complexity classes would be the same is kind of obvious if you have a multi-way system that is kind of trivially causal invariant. So for instance, if you have a multi-way system where everything eventually converges to some normal form, then obviously it's going to be the case that if you can reach some state if you can reach a sufficiently far away state with a non-deterministic rule, you could also reach it in roughly the same number of steps with a deterministic one, because eventually they will reach the same state anyway. But then in less trivial cases, basically the rate of multi-way branching therefore puts constraints on the extent to which, say, P and NP can be related. And so at some level, you can think of these questions about relations between complexity classes as being questions, if you formulate them in terms of physics at least, you can think about them as being questions about the branching rates of different multi-way systems. With respect to quantum computation, then,
let's take the classical case for a second. I mean, so in a sense, the multi-way graph is a map of the possible paths of a non-deterministic computation. And so one of the claims would be, if there is NP completeness, what does it mean for the structure of the multi-way graph? Because, for example, we can immediately say that, so for example, a typical NP complete problem. So first of all, one problem is that NP complete problems are usually stated in terms of, true-false test type problems. I suspect it's a slightly different complexity class that we want to look at in terms of what's generated by the system. But so the question would be, as you change the problem, as you make the integer longer that you're factoring or whatever, which we don't know to be NP complete, but whatever, how does that affect the structure of the multi-way graph? And can we see that, what aspect of NP completeness and the story of NP is about time complexity. What we've got in the multi-way graph is this kind of bushiness factor, this kind of, this treeing out, the branching factor. So how does the branching factor enter kind of one's thinking about, P versus NP and so on? I mean, so in other words, what we're thinking about is a single thread, right, is going to be something that, the length of a single thread is what's measuring the traditional, that's the polynomial time, or, that's the time complexity of the thing. The question is, when we have an NP problem, we know that we're branching things out. And the question is, what can we say? And for example, does it, for physics, we assume, since we believe the underlying rule will have computational reducibility and things, we will immediately get a bunch of NP complete type problems. So, so here's another question we could throw out. If we think about quantum mechanics, for example, what is a problem, a standard quantum mechanical problem, which we can now readily see will be NP complete? So, sorry, we're turning this into a working session where we're actually trying to figure stuff out. But so we'll come back when we get more questions here. We'll come back to other people's questions. But that's
a good question, though.
Yeah. Let's think about that for a second. I mean, the question is, what kind of quantum questions are, we're really asking, is there, a typical NP type question would be, is there an eigenstate that has certain properties? Is there some single thread that has certain properties? And then what can we say about, how can we determine what, in this model, then we have a notion, we can say, given that we have a model for quantum mechanics, we can ask, in terms of classical computation, what is an NP, what's an example of an NP problem, and then potentially NP complete problem. But maybe we should talk for a second about the quantum analog of that, where we're looking sort of across the whole branchial surface, so to speak, and where we have the superposition, and we're trying to, look at the way the superposition evolves. And I think you were going to tell me about complexity classes that are after my time, so to speak. So I don't know the names of all the quantum complexity classes, but what are the relevant quantum complexity classes?
Well, so in this case, they would be things like BQP. So there are essentially for every classical complexity class there is a bounded error quantum analog of that complexity class. So what you're basically saying is, if you set some epsilon and you want your quantum computer to be able to solve this problem within epsilon, could it do so with a number of gates that scales roughly, polynomially or exponentially, factorially, whatever the complexity class is. So then there are a bunch of these complexity theoretic questions about how the quantum complexity classes and the classical complexity classes relate, which is kind of what you were alluding to. And you're right that actually potentially the branching structure of the multi-way system and how these branch-like hypersurfaces grow potentially gives us ways of determining cases where there will be difference between the quantum complexity class and its classical analog, because effectively what you're saying is that when you perform a measurement on your multi-way evolution graph, so you effectively collapse things back to a single evolution history, to a thread of a single evolution history. That process in itself is computationally irreducible, right? That requires a non-trivial number of computational steps, and so there's a trade-off to be had between the exponential gain you get by running a quantum computation and this kind of potentially exponential loss you get in the process of performing the measurement when you're doing these completion procedures and collapsing the evolution of the multi-way graph, and that gives us kind of potential for placing bounds on the extent to which quantum and classical complexity classes can be related, but we haven't yet explored that in detail.
So let's talk about bounded error. What you mean by bounded error. So we've got this branch-hill graph, and it has certain weightings on it, and so bounded error means what with respect to the weightings of on the branch-hill graph?
That's a good question. So what you're basically saying is, when we do this, this completion procedure it's kind of a coarse graining procedure, right? It's definitely not. It's not a kind of fine grained thing. So when you do this completion procedure, the eigenstate that you're kind of collapsing down to may not correspond precisely to the eigenstate that you were kind of attempting to measure. So it's effectively because the process of constructing one of these branchial black holes that Stephen was talking about, this is a messy, complicated process that requires large amounts of energy input and so on. So it's not going to be an exact thing in general. And so the completion procedure sort of introduces a certain degree of coarseness. And the question is, what degree of coarseness are you able to tolerate? So the measure gives you the natural measure defined on the multi-way evolution graph, I think, gives you a way of quantifying how far away from the true eigenstate did you actually end up being, and that's kind of that's the notion of this bounded error sort of.
Well, so you think that the error can be thought of in terms of actual distance in branch-hill space?
I don't see any reason why not.
But that's interesting. I mean, but that can also be thought of in terms of these entanglement distances and entanglement entropies and things like that, right? So what is the relationship normally between that notion of bounded error and the concept of these entanglement distances and so on?
So I don't know offhand. There may well be one. I'm not aware of one. Conventionally in quantum computing, when people talk about bounded error, what they're talking about is kind of if you performed repeated measurement, and you get some statistical distribution, effectively that you're querying properties about that statistical distribution of possible measurement outcomes. But given that that distribution basically corresponds to a small kind of some kind of hypersphere in a branch-like hypersurface, I think it should be entirely possible to formulate that purely in terms of distances on the branch-like hypersurface, but we don't yet have a formalism that describes that. And so there's potentially quite a lot of fruitful, quantum complexity theoretic research to do there, particularly if this hasn't been explored.
Let me turn to a different thing. You talked about gate-type complexity for quantum computing. The question would be, in a multi-way graph, how do we map the sort of complexity measured in terms of gate numbers into the structure of the multi-way graph? So
right.
In other words,
sorry, go on.
Yeah. So I mean, in normal quantum computing, the complexity measure is, in classical computing, it's the number of steps of the Turing machine. In quantum computing, it tends to be the number of gates you're going through. So my question is, how do we think about this computing in terms of gates, in terms of the multi-way graph, and is there an obvious way to do that?
Yes, right. Okay, so actually, let me mention something that I figured out while I was working on the Wolfram language quantum computing framework. That I suddenly had this moment of realizing that I understood quantum computing better as a result of working on this project. So one thing I realized was that, okay, so in standard quantum computing, you have the notion of like you have sort of gates, which are your kind of evolution operators, and then you have measurements, which then collapse your evolutions. And I started to realize what those kind of corresponded to, with respect to these multi-way evolution graphs, that basically quantum gates or quantum operators more generally are updating events that map between neighboring branch-like hypersurfaces, whereas measurement operators are updating events that map between events on the same branch-like hypersurface. So in other words, if you're mapping between events on the same branch-like hypersurface, that's a collapsing process, right? This is what you're doing when you apply these Knuth-Bendix completion procedures. You're constructing these new update rules between states on the branch-like hypersurface that impose equivalences that eventually collapse the multi-way evolution graph down. That's the analog of a measurement. But then when those updating events are actually connecting the neighboring branch-like hypersurfaces, then you're evolving in time or with respect to some universal time function. And that's the analog of a quantum operator. And so the argument would be, if there is this correspondence between multi-way evolution graphs and quantum computers, then that somehow every quantum gate, every quantum, that would exist in a quantum circuit can be thought of as some composition of updating events that connects neighboring branch-like hypersurfaces.
But when you say connects neighboring branch-like hypersurfaces, you're saying those are time-like edges, basically. The time-like edges in the multi-way graph connecting successive branch-like hypersurfaces, right?
Right.
As opposed to, you're saying measurement events, you're saying are things that are in the branchial direction.
Yes, although, okay, there's a subtlety here, because what I've just stated is kind of the way that you conventionally think about measurement in quantum mechanics. You think of it as being a sort of an instantaneous thing. So in that case, it would just be those edges would be purely in the branchial direction. But we know that that's going to violate certain hyperbolicity properties of our space. And actually, one of the implications of our model is that you can't do instantaneous measurement. Every measurement takes at least one elementary time. So actually, okay, so what I just said was kind of an approximation to what I think the actual truth is, which is that they're not quite in the branch-like direction, but they're sufficiently tilted that you can take them as being very close to being in the branch-like direction.
But the whole point is that what you're saying is, if we're trying to work out time complexity of something like factoring and doing the measurement on factoring, this effect that you can't have a perfect, it's like you can't have infinite propagation speed in space, you can't have infinite propagation speed in branchial space. That's exactly the thing that gives you a time that it is required to do the measurement. That is the fact you can't have essentially this horizontal motion in branchial space, that it has to have some vertical component that's in the time-like direction, is the thing that's telling you that you can't actually do the instantaneous measurement, right?
Yes, right, precisely.
So I mean, in a sense, what's being said there is that what you're saying, so that's interesting, that the traditional quantum gate is a purely time-like operation without branch-like, which has no, I mean, which is well, I guess it's a purely time-like edge, or it's a time-like edge which has, it's a time-like edge, basically, or at least it corresponds to a. And by the way, what then is the relationship? I mean, something that came up yesterday, which I'm kind of shocked I hadn't thought of before, but the relationship between energy and computational effort. So insofar as energy is the flux of causal edges through space-like surfaces, that energy, if we're now identifying quantum operations, quantum gate operations, as corresponding to time-like propagation, which means causal edges in the crossing space-like hypersurfaces, that implies that that process involves a certain energy density. Right? So what is the relationship in traditional quantum computing? One's imagining there's a Hamiltonian that's sort of pushing things forward, so to speak. But what's the relationship between the presence of that Hamiltonian and energy density in the system?
That's a good question. I will need to look that up. There definitely are results about them, but I don't have about that question, but I don't have them on hand.
All right, but anyway, we're talking about. I mean, I think this interpretation of yours of, the gates are the time-like edges, the measurements are the branch-like direction things, and then because we have a maximum entanglement speed, we have a maximum rate of measurement, which should give one a bunch of bounds on essentially given a, because then the question is this: let's say you're doing an NP-complete problem. And that NP-complete problem involves essentially treeing out a large number of possibilities. Okay, so we've got essentially this exponentially broadened tree. Well, then we're trying to corral that back to measure something. So effectively what we've got to do is we've got to go exponentially far in branchial space to be able to make that measurement, to be able to find that, that factor of that number or whatever it is, right? And so but we now know that to go that distance in branchial space takes some time because there's a maximum entanglement speed. And therefore, then the question will be, in branchial space, what is the dimension of branchial space? Because that will determine how quickly you can go, how many time steps effectively it takes you to go a certain distance in branchial space. I think we can figure this out. I think we can actually figure out a bound. So, when you're trying to solve NP-complete problems with a quantum computer, there is this issue of, corralling the measurement, so to speak. I bet we can get a bound on how long that takes. And I bet that the answer will depend critically on the structure of branchial space. That is, that if branchial space was finite dimensional, I think you'd be toast, so to speak. So my claim is, if branchial space was finite dimensional, then solving an exponentially treeing out problem, the measurement process would inevitably take exponential time to reach that point in branchial space, because there's a maximum entanglement speed, and to reach that point in branchial space would take exponential time. The only way that you'd get somewhere is if branchial space is not in fact finite dimensional, and that therefore you can reach that point, in some piece of branchial space in less time. Anyway, that's been my thought. All right, we got some questions on the live stream here, so let's take a look.
Is it worth mentioning something about maximum rates of entanglement in conventional quantum mechanics, or should we?
Sure, go ahead.
Okay, so yeah, we should just quickly mention that the thing that we're proposing, as Stephen says, is a sort of definite prediction, or potentially a definite prediction, of our models with respect to quantum complexity classes and things. But actually, this idea that there might exist a maximum rate of entanglement or a maximum rate of measurement has precedence in the sort of standard formalism of quantum mechanics. There are various theorems. There's this thing called the Lieb-Robinson bound. There's a related thing called the Margolis-Levitin bound, which basically give you bounds that are roughly proportional to the value of h bar on the rate at which quantum entanglements can kind of propagate. And that's sort of the analog of our speed of light in branchial space. If you make some propagation in branchial space, how quickly does the sort of entanglement cone spread out? Basically the kinds of velocities we're talking about there turn out to be compatible with things like the Margolis-Levitin bound. It's also worth saying.
Where do those bounds come from? Where does that bound come from?
So the basic idea is you imagine you have some quantum state, and then you do some kind of expansion of its Hamiltonian. And then you compute a survival probability, and then you show that as you allow the entanglement rate, I may be mixing this up with the quantum Zeno effect. No, I don't think I am. As you allow the entanglement rate to go to infinity, you can prove that the rate of evolution kind of goes down, and eventually those curves kind of cross over, and you can show that the state has to sort of that as you try to increase its entanglement speed, eventually the evolution of the state has to freeze at some point. And it's related to this quantum Zeno effect that says that as you apply successive measurements of a quantum state, its survival probability approaches 1. So it's basically it can't evolve any further beyond a certain point.
Interesting. Okay, all right. Let's take a look at some of these questions here. We're developing all kinds of questions. Can we simulate quantum computers using multi-way graphs? I think we've been just talking about that kind of thing. How expensive is quantum computing? Not sure in what measure. I mean, we're talking about kind of various kinds of measures of expense for computing. Is this project just a newer kind of computer science? Well, we don't think so. And it's only insofar as computers are everything and the whole universe is doing computation. Okay. How large of a quantum computer would be needed to falsify this model? Well, gosh, that's hard to say. I mean, there's this. I don't think it really helps to have a quantum computer. And in fact, one of the things we're realizing is that there are bounds on what quantum computers can do in this kind of model. Okay. Let's see. I think we're getting a bunch of quantum mechanics questions. We should not have started this off talking about quantum computers, because we're going to end up with a repeat of discussing quantum mechanics here. Okay, hold on a second. There's a question here. Is there a way to create a collection of relations between a collection of rules? Not not sure what that is. Okay, so Colt here is asking, what are your thoughts on genetic algorithms based on string rewriting systems? Well, okay, interesting. I mean, so one of the problems with genetic algorithms is it's hard to make incremental changes to programs. String rewriting systems are one of the only places where it is even vaguely plausible to easily make sort of incremental changes to programs. I mean, in neural networks, for example, the incremental changes are all done by adjusting these continuous weights of the neural net. In traditional programs, discrete programs, it's much harder to make a small change to the program, but you can do that with strings. Now, I think, we have some sort of embryonic ideas about actually things to do with more like modeling biological evolution in terms of multi-way graphs. And this is very embryonic, so I'm not even sure we should talk too much about it. But one of the things that I find really interesting is that essentially, it's a little bit like when I worked on cellular automata, starting in the 1980s, these were sort of very, very minimal models of things that had just arrays of values and evolving in time. And those very minimal models turned out to have applications to all kinds of things. I mean, I just was amazed at these sort of the first 256 rules. Pretty much every single one of them has been applied to something: earthquakes, traffic flow, catalysis, all kinds of different things. So like the more simple the model is, the more likely it is to have applications. Well, so these models that we're looking at that involve, rewriting of hypergraphs and so on, they're a bit more complicated for us humans or even our computers to wrap our arms around, so to speak. But now that we are really getting into these models, it's becoming clear that they are also actually useful models for a lot of other things beyond fundamental physics. I mean, we sort of, came up with them for purposes of fundamental physics, but they're useful for other things too. And I think, one of the big areas I think is going to be distributed computing and understanding a bunch of things about that. And hopefully we can talk about that a little bit here. But I think one of the other areas that's really a weird one is thinking about biological evolution, because essentially what's happening is that in biological evolution is you're making something like a multi-way graph. You've got different. You're making kind of so you've got multiple different things that can happen from a given organism, and you're ending up with some whole graph of possibilities. I don't yet understand this very well, but this is a the intersection of multi-way graphs, string rewriting, genetic algorithms. That's interesting. So I suppose what you would do, okay, how would you apply a genetic algorithm to string rewriting done in a multi-way graph? I think what you would be doing is applying a fitness criterion on the multi-way graph. So yeah, this is what you're doing. You're basically pruning the multi-way graph. So you've got this multi-way graph, it's treeing all these possibilities out, you've got all these possible rewrites, but you say, well, I've got a fitness function, and the fitness function is going to say that every critter that ended up with a string that starts with an A is not going to make it. So that means you're chopping off a bunch of that multi-way graph. So now, if we think about that in terms of our branchial space, which is something that one hadn't really looked at in sort of string rewriting systems, to my knowledge, in anywhere. I mean, that's something that we sort of invented for thinking about quantum mechanics. So what that's then saying is, yeah, okay, so this is interesting. Okay, so the basic idea would be that when one of the issues in talking about evolution often is, what is the space in which things evolve? You say, my genome evolved. Well, it made some changes in the genome, but what consequences did that have for the phenotype and so on? Well, one of the things that you're seeing here potentially is, is this notion in this branchial space. You are effectively saying what is the, what you'd be saying by talking about, you're talking about fitness, and you'd be saying there's a particular region of branchial space that is unfit, so to speak, and so you'd be ending up sort of directing the multi-way graph to have more for its multi-way edges to survive in going through one part of branchial space, but not going through another part of branchial space. And that kind of makes me wonder, I mean, you can imagine sort of a fitness, you can imagine niches effectively in branchial space where the multi-way edges will survive, corresponding to organisms that survive and other ones that don't. Okay, there's an interesting theory to be made of this. This is we're going slightly far afield, but I think that's actually, somebody should research that. That is an interesting, the relationship between multi-way systems, branchial space, genetic algorithms, that is an interesting thing to look at. Thank you for that question. Okay. Let's see. If the model is proven right, does the model imply that P is not equal to NP? No, it does not address that issue. P not equal to NP is essentially a mathematical question about the behavior of Turing machines, or equivalently the behavior of other kinds of computational models that are polynomially related to Turing machines. My own personal suspicion is that P equals NP is not decidable in the standard axiom systems of mathematics. And part of the reason I say that is you can sort of do an empirical investigation of P versus NP. You just say, take all the Turing machines of a certain size and ask how well they can solve a problem and how well they can solve it, and take all the non-deterministic Turing machines of a certain size, how well can they solve the problem? Well, I've done that in certain cases, and you can just make empirical results, of a problem of this size, how well did the best Turing machine do? And you might think, oh, you're going to get something where there's a nice smooth curve and you're going to be able to figure out, oh, this curve is always bigger than that curve and so on. But no, that's not what happens at all. You get this incredibly wiggly kind of thing. I mean, you can't take it very far empirically because the number of Turing machines, as you increase the size and so on, grows very rapidly. But insofar as you can work this out empirically, you can see sort of why it's hard to figure out whether P and NP can be the same asymptotically, because you have this thing that's wiggling all over the place. And it has kind of a, to me, it feels a lot like problems in number theory and in group theory and so on, where in the end, they turn out to be undecidable, independent of the axioms of the sort of standard system of mathematics. So that's my guess for P versus NP. I don't think it's not my favorite problem formulation either, because it's kind of in the end, it's kind of messy, and it has a bunch of footnotes about things being sort of polynomially related to Turing machines and so on, which I don't consider to be the cleanest way of setting things up. Okay, next question. Do you think Fredkin gates are possible to make? Out of what? Out of, I mean, one of the issues is that in these models, one's being very sort of realistic about the measurement process and about maintaining purity of quantum states. And I think that one of the things that looks to be the case is that sort of maintaining the purity of quantum states takes energy. And I don't know whether that's something that's sort of known in the quantum computing literature and so on, but is that, Jonathan, do you have a comment on that?
Yeah, so I mean, this is similar to the question you asked earlier about Hamilton. I mean, it's certainly the case that the structure of your Hamiltonian when you construct one of these circuits implies certain things about energy densities and so on. But I'm not sufficiently familiar with that literature to know what those bounds are. But basically, yeah, as you say, within our models, the trade-off between sort of computational effort and energy density is some question about some asymptotic question about, for every evolution edge in your multi-way evolution graph, roughly how many new causal edges get spawned as a consequence of that evolution edge.
Yep.
And so that gives one a sort of a ratio of computational effort to energy density.
Right, which is interesting. I mean, remember, it's energy density. It's not, but what's different here is people thought in the early history of kind of theory of computation that it might actually take energy. You might dissipate heat by doing computation. That's not what we're talking about here. We're talking about the presence of energy density to maintain that there needs to be energy density in order to maintain the fiction of a pure quantum state, basically. In order to maintain so what's the analog of that? In general relativity, for example, what's the analog of that? Maintaining, the freezing time analog for and something like an event horizon. What's the analogous idea for the sort of expending energy to do that?
I strongly suspect it's basically black hole evaporation. So what's happening in when you try to maintain a pure branchial state, it's like you're trying to maintain either, well, depending on whether it's a measurement or it's a genuinely pure state, you're basically trying to maintain some kind of event horizon around that branchial state. And if that's a physical event horizon, then that requires a certain energy to maintain. Because, okay, if you now go to the relativistic case, as Stephen mentioned, if you're trying to maintain an actual physical event horizon associated with a physical singularity, we know that it will, we have strong reason to believe that it will undergo this process of Hawking evaporation. And so if you want to maintain that event horizon at the same size kind of indefinitely, there's a certain minimum amount of energy you have to keep throwing into that black hole in order to maintain it. What we conjecture is that there's a similar effect going on in branchial space, that by trying to construct one of these branchial singularities with an event horizon to maintain it over arbitrary timescales, which is what you need to do if you're trying to build a serious quantum computer, you need to keep injecting more energy to basically fight off causal edges that will be causing that singularity to evaporate. So there's a certain, so basically the analog of quantum decoherence in a practical Turing machine would be effectively Hawking radiation occurring in branchial geometry, which is, I think, quite a nice prediction.
Well, so let's talk about that for a second. I mean, the maintenance of a black hole, back in my day, people were very surprised that black holes could evaporate at all. But what you're saying is to maintain the black hole from Hawking evaporation, you need to, what is the rate of throwing more matter into a black hole that you need to have to avoid Hawking evaporation?
I mean, it's very, very minimal. So even the timescales over which black holes would actually evaporate are, we're talking sort of cosmological timescales here. So the actual incoming energy density to a gravitational black hole that you need in order to maintain it is absolutely tiny. One of the interesting things, though, is that in branchial space, our kind of effective speed of light, which is the speed of entanglement that we described earlier, is much, much faster than it is in ordinary space-time, right? Our bound on entanglement rate is much higher than our bound on the speed of light in the causal graph. One of the implications of that is that one would expect there to be faster effectively faster event horizon evaporation effects occurring in branchial space versus in space-time. So once you're dealing with maintaining a pure quantum state, you actually really care about having to do that maintenance.
So let's just work this out for a second. So what is the actual rate of Hawking evaporation? And I mean, towards the end of a black hole's life, as it gets smaller and smaller and smaller, the rate of evaporation gets quite large. What is it in Planck units? Do we know this without looking it up? We can look it up, presumably, but it must be related to the Hawking temperature.
I forget the exact formula. I think it's 1 over the square root of like 2 times the mass or something is the Hawking temperature.
Okay, but the point there is that there's a formula that involves the speed of light that is the amount of energy you need to put into a black hole to balance Hawking radiation, basically.
Right.
And that will depend on the speed of light. Now, similarly, although we don't have quite the same situation, we would expect that the maximum speed of entanglement, the thing we're calling zeta, will play the same role as the speed of light. And an analog, and in fact, what will happen is, just like there's a G, which I'm sure appears in the Hawking evaporation rate, that the analog of that will be, because zeta has different dimensions. I mean, okay, what we're about to try to work out is what the actual rate of putting energy to maintain a qubit is. And I think that will be an interesting thing to work out, because we don't actually know that that's out of experimental range, so to speak. I mean, the maximum rate of entanglement, our best initial estimate of that is 10 to the 5 solar masses per second, which is kind of ridiculously huge on the scale of your typical laboratory quantum computer. But insofar as one's trying to maintain a qubit, it's not completely obvious to me, and it's not obvious to me there won't be a factor of psi, the multi-way multiplier, that could really change the value of zeta down to something much more experimentally accessible.
Yeah. By the way, I just looked it up. So it's on the order of c cubed over m. Is the Hawking temperature for a Schwarzschild black hole?
Well, in what natural units? With G equal to 1 or what?
Yeah, with GH bar KB all equal to 1, and there's a factor of 8 pi in there as well. But it's.
So wait a minute. So you said c cubed over m?
Yes.
And but that's the factor of c, where we've got a bunch of other things set to 1. So we have to do a bit more work to work out what the analogous. But so the calculation to make is what's the rate of branch pair related evaporation of a qubit, right? Because it depends on the branching rate of a single qubit, and how many edges. So roughly what's going to happen is, because the entanglement cones have an opening angle that's related to zeta, which is very, the opening angle, they get very big very quickly. And then, so the question then is, what do you have to do? And so each of those entanglement cones has a certain amount of energy associated with it. All right, we have to work this out. This is an important homework exercise. We need to know how much energy it takes to maintain a qubit. This really, and there may be somebody on the live stream knows literature that exists on this. I mean, essentially, this is going beyond. In traditional quantum computing, like in the quantum computing framework that we're making for Wolfram language, we're not being honest about the Hamiltonian, so to speak. We're just saying there's a unitary evolution operator that describes, the time evolution of the system and represented in terms of gates and so on. And we're not saying you implement those gates by actually having this energy function in there. And the interface to the more realistic energy function, I'm not sure how well understood that is. I think back in my little effort in quantum computing back in 1981, we were thinking about that, and we got very confused because it's difficult. For example, when you think about a quantum cellular automaton, there's this trade-off. It's very easy to make a quantum cellular automaton at the level of the S matrix or at the level of the unitary evolution operator. The correspondence between that and the Hamiltonian is complicated. You can't both have locality, and I'm not sure that's ever been solved, locality both in the unitary evolution operator and in the Hamiltonian. All right, more questions here.
Right, so my point was only that because one has this apparent cubic dependence on the maximum signal velocity, we can reasonably expect that these qubits in branchial space will be very hot. They will have very high evaporation temperatures if the rate of entanglement is high.
So what do you conclude from that?
Therefore, they will evaporate quickly. That the decoherence is a problem for quantum computers, which we kind of knew already. But
right, but the question is, can we make that quantitative? And one thing we've got now is a new sort of constant of nature, this zeta quantity, which and the question is, how does that relate to? Which I think is simply a new constant. It is not related. You can't get it from H bar and C and all these kinds of things. It's an independent object, and so that presumably will enter somehow in working this out for quantum computers. All right, we've got a long question here. Gosh. Well, the question here from, I can't read these handles, SAI, I'm going to call it. The question is about relationship between our kind of network-based models and thinking about connectionist models and neural networks and so on. Okay, good question. You're throwing me into kind of a weird, you're making me remember that on April Fool's Day of, what was it, 2 years ago, maybe now, I wrote this this piece about buzzword convergence of, let's see, blockchain, neural, quantum, AI, and what that could possibly mean. And I realized that some of the science of those things was deeply connected. So a question that one might ask here, I suppose, is what's the relationship between kind of what happens in a neural net and what happens in, for example, these multi-way graphs? Gosh. It's kind of an interesting question, actually, because in a neural network, what you're doing is, you have a set of weights, and you're asking, interesting. So I mean, looking at quantum evolution and looking at neural net evolution, they're both sort of exercises in linear algebra. One difference is that in the neural net case, it's very important that there's a nonlinear piece to it, that you do the multiplication and then you apply the ReLU or something, you apply the ramp function. You don't have just the linear evolution. Whereas in quantum mechanics, it is more like you are just doing the linear evolution. So I guess the question would be, what's the relationship between, is there a formulation of kind of what happens in the multi-way graph and the way in which you're essentially you're combining, let's say you've got weights on every edge of the multi-way graph. How do the successive steps in the multi-way graph compare with the kind of operations that you're doing on sort of successive steps in a neural network. I mean, one place where we've seen this is in making up framework for quantum computing and comparing that with the framework we have for neural nets. There are certain similarities. I don't know, Jonathan, have you looked at the, I mean, so you know, we might have a linear layer, or this layer, or that layer. It looks very much like the gate structure of a quantum computer, but it's different because in a quantum computer, first of all, we're looking at the thing that we're representing in a quantum computer is a Hilbert space. We're representing points in a Hilbert space, whereas in the neural net case, we're representing we've got a vector that represents the state of some array that represents the state of the neural net. And then after it goes through the next layer, we've got a new state of the neural net. But that transformation is typically a nonlinear transformation. It has an important part of it can be linear, but then there's a nonlinear piece that's added on. Whereas in the quantum case, we're always imagining, I think, that we've got, but actually, you know, having said that, what happens when there's a measurement? Measurement is not a linear.
Well, yeah, I mean, the projection onto an eigenspace is not generally viewed as a linear transformation.
Right.
That's an isometry.
So then the question is, what is the analogy between the nonlinear operations that you do in a neural net and a quantum computer? Because often in quantum computers, it's like gate, measurement at the end. But if you don't say that, if you say it's gate, measurement, gate, you know, if there's if measurements become a sort of routine thing in the quantum computer, which may be more like the real case, particularly if you can't maintain that qubit with perfect, you know, coherence, so to speak, then what happens when you have these projection operators being applied in the middle of doing this essentially linear algebra? And what is the analogy between that and what you see in a neural net? Those are good questions. I mean, I think, you know, a big difference, of course, with the whole neural net story is that in neural nets, you are really trying to do this inversion problem, and you're trying to say, I want a neural net that will perform this set of transformations on its inputs, and I'm going to tweak the weights in the neural net to achieve that. Whereas in quantum computers, we're not, at present, that's not the way you program a quantum computer. The way you program a quantum computer, well, having said that, one of the things that people are often interested in doing is saying, I'm trying to achieve this transformation, break it down for me in terms of gates. And the operations that do that are not, I mean, I think you could actually imagine using neural nets actually to do that operation. I don't know. What is the typical way, the decomposition into kind of specific gates? How is that done? Is that a linear algebra play, or is that something different?
That's this is basically the problem with quantum circuit compilation. And yes, that's a kind of fancy linear algebra play. There are variants of things like Schmidt decompositions and things you can do to basically solve this generalized matrix factorization problem of, you know, that you've got some big matrix, you know, it's composed of a bunch of random gates, and you're trying to figure out to within some epsilon what gates it was composed from. So it's basically a matrix factorization problem with an error term, at least in the quantum computing case.
Is that right, or does it end up being something more like a combinatorial optimization problem, which becomes much more neural netty? I mean, is it combinatorial optimization, or is it some linear programming type of thing?
There definitely are linear programming formulations of it. It wouldn't surprise me if there are combinatorial optimization sort of formulations of it, because there are ways you can formulate matrix factorization in terms of combinatorial optimization. Things like matrix factorization over semi-rings, that's known to be over certain classes of semi-rings, that's known to be a combinatorial optimization problem.
Okay, interesting. All right, let's keep going here. Well, we'll be talking about topological data analysis. Boy, you guys are throwing us all kinds of funky stuff. Is topological data analysis even vaguely relevant? Okay, let me mention something that is sort of relevant there, which we thought was going to be relevant, but turned out not to be relevant. Given a hypergraph, that where you just have connectivity information, to what kind of ordinary dimensional space does it correspond? What is the best way to reconstruct a what's the best way to reconstruct, best way to embed an arbitrary hypergraph in space? And we had thought that some of these topological data analysis reconstruction techniques might be relevant. It didn't seem that was the case. I don't know. I know, but Max might possibly have a comment on that. I'm not sure. Or any comments on this? Because we tried doing a variety of kinds of reconstruction techniques the I mean, the main issue is you've given connectivity data to what, okay, what you're trying to do is you're given a graph and you're asked the question, there are certain, given 2 points in the graph, there is a certain graph distance between those points. The mathematical problem is, can I lay that graph out in space in some number of dimensions so that the distance in space, in that space, with the metric of that space, agrees with the graph distance? So in other words, if I had a grid, I could easily lay that out and so that the graph distance, well, actually, then the distance ends up being Manhattan distance, so it's a little bit tricky in that case. But qualitatively, what one's wanting to do is one wants to figure out in what number of dimensions can one lay the graph out so that the graph distance agrees with the distance in the space. And that's a problem that is not unrelated to the kinds of things that come up in topological data analysis. And we tried to use some of those techniques to do reconstructions of these graphs and didn't work out at all. So that's so we don't know the answer there. Okay, question here: is the smallest possible universal Turing machine related to the fundamental theory of physics? I don't know. I mean, we found, I had this this conjecture about the simplest universal Turing machine, this 2-3 Turing machine. And back in 2007, we had this prize for somebody to prove or disprove that it was indeed a universal Turing machine. And Alex Smith succeeded in proving that this tiny Turing machine is universal. And we know, because I looked at all simpler Turing machines, that it is the simplest universal Turing machine. Does the fact that that is the simplest, that's an interesting question, actually. I mean, so the issue is, given a representation of computation like Turing machines, and our universe, we already pretty much know that our universe is a universal computer. Anything below that, our universe would have only trivial behavior, and we wouldn't be able to get the kinds of things that we see in the universe. In terms of our rule space relativity, it would correspond to the universe would be a reducible black hole, so to speak, in rule space. So assuming that isn't the case, we kind of know that the universe is capable of universal computation. Then the question is, in the space of Turing machines, we actually know what the simplest, with respect to number of states and number of colors, what the simplest universal Turing machine is. And so you might say, well, does that, that's a good question. It hadn't occurred to me, actually, does knowing the boundaries of universality in, for example, Turing machine space, what does that tell us about sort of the boundaries of what plausible models for physics might be? Okay, so I think a more directly relevant question would be this one. What is, which is actually one, this is a good question, we should answer this one. Okay, what is the simplest, hypergraph rewriting, one of these things we're calling Wolfram models, simplest, hypergraph rewriting Wolfram model thing that is universal? Good question. Don't know the answer. That would be a good thing to figure out. I mean, okay, I'm going to go out on a limb. I'm going to say, I think it will be a, okay, the first mantra is the computational animals are always smarter than you are. So if I say this is there's, there couldn't possibly be a universal one in this group of rules, I'll almost certainly be wrong. But I would say that I will be confident that there is a universal one in the 2-3 goes to 3-3, which means a ternary hypergraph with two ternary relations. So 2 ternary hyperedges transform to 3 ternary hyperedges. I will make the claim. Actually, I'm going to make even a simpler claim. I think probably there's one in 2-2. I think I'm safe in claiming there's one in 2-2 goes to 4-2, which means 2 binary edges going to 4 binary edges. I would predict that there will be a universal, that there'll be something capable of universality in that space. Now, the question is that sort of first universal rule likely to be a rule that aligns with our sort of description language used in physics? I kind of doubt it, but I don't know. I mean, again, I got to remember, I've been trying to keep this mantra for 40 years. The computational animals are always smarter than you are. Every time I say it couldn't possibly do that, I'm almost always wrong. But yeah, that's an interesting one. Okay, question here from Colt. Could these rules have applications in reinforcement learning? I think this idea, so, you guys are making me think, one of the big problems with neural networks is there isn't a good global mathematical theory of what's happening in them. And I am sort of wondering whether there are things that can be said on the basis of multi-way systems and branchial space and all these kinds of things. Because, okay, okay, there's a little bit of a thought here. So one thing about neural nets is you are usually concerned with a single thread of history in a neural net. That is, you say, I've got this neural net, I'm going to train the neural net based on this input, I'm going to do gradient descent, I'm going to do this. But there actually are many possible trainings that you could do, and you're often picking random numbers to do that training. So a question would be, usually in neural nets, it's hard enough for us to figure out what's going on when one's looking at a single thread of history for the neural net. But the thing that one might imagine, which I've not really thought about before, is what if you go full multi-way and you look at all possible evolutions, all possible trainings of the neural net, and you try and make statements about this giant space of all possible trainings of the neural net. And for example, what can be said about, are there analogs of things like causal invariants in the training of neural nets? And is there a way to think about this kind of giant space of all possible trainings of that neural net? And what can you say about it? And for example, in the space of, normally one thinks about, attractors in the space of inputs to the neural net, but I'm wondering, what if you think about the whole neural net itself and the space of all possible neural nets, the ensemble of all possible neural nets? What can you start to say about that kind of setup? And are there analogs of some of these? Because the main thing that we're doing in this approach to physics and so on is we're saying, look, there's a huge number of degrees of freedom. There's a huge amount of sort of treeing out of all these exponential things, but there is also this regularity that is particularly associated with causal invariance that allows us to basically, in mathematical terms, mod out a lot of things and take us down to something that we can actually kind of wrap our arms around. But we get to that by first sort of treeing everything out and then looking at these kind of slices. And I guess I am now wondering, good question, whether one might be able to do some similar kind of thing in neural nets, as I say, thinking about the ensemble of all possible neural nets, rather than thinking about like ensemble of possible inputs and so on for a specific neural net. So interesting thoughts. Let's see. Okay, from Phoenix, what subfields of computer science and physics are necessary to learn to meaningfully contribute to this project? So I think the decent answer to that, in terms of computer science, things about term rewriting, that's the theory of, things that show up in automated theorem proving, things that show up in, in those kinds of areas. That seems to be a very relevant area. Now, the literature in those areas can get pretty technical, and I'm not sure how much of the technical aspects of that literature are that important. I don't know, maybe Jonathan has an opinion about that. I mean, I think there are, I probably don't know. I thought I knew the literature of term rewriting, and I didn't think it was. One feature of term rewriting is that the basic results of term rewriting have been rediscovered at least 5 times. And they go under completely different names, like Grosvenor basis reduction, like the Knuth-Bendix algorithm, like the Church-Rosser property. All these things are basically the same idea, and they've been rediscovered in different subfields, and often with incredibly ornate, to my mind, it's a case where mathematical notation is not particularly successful. A computational language is perfectly easy to express these things in, but the mathematical notation gets pretty bizarre. And, so these things are a little hard to read. Jonathan, do you have a comment on that?
No, I agree with basically everything you said. I mean, but I personally suspect we're about to see a kind of Cambrian explosion of sort of term rewriting related results because there's suddenly so much renewed interest in kind of interactive theorem provers, proof assistants, things like that, and people are finally. There was a spurt of activity in those kinds of things in the 80s and 90s, and now I think we're finally going to see another big spurt of activity. So maybe a whole bunch of term rewriting results are about to be rediscovered.
Right.
I did notice, by the way, I think we have a question coming up about the relationship between causal invariance and confluence in term rewriting. So maybe we should save the technical.
Okay, all right, more detail. But I think the thing to say about our use of term rewriting is that one of the things that we're doing is we're doing term rewriting in bulk. I mean, we've got, it's not like we're just doing one little term rewriting thing. We're talking about, the space of all possible term rewritings of things and so on, which is something that has been kind of, I think, not, that's not been the focus of what people have looked at in the term rewriting literature. But the question we're trying to answer here is what areas of physics and computer science are worth studying to contribute to this project. I would say an understanding of general relativity is highly useful, and a lot of the ideas of general relativity and the notion of the kind of structures that are talked about in general relativity are useful. In terms of quantum mechanics, an understanding of sort of the formalism of quantum mechanics, I think the cleanest versions of that probably are the ones that show up in quantum computing, those are also useful areas. I would say in terms of education, we have a summer school that we've been doing for the last 17 years, which has been about science and technology and so on. And we were planning this year, we were going to have a physics component to it. This year, the summer school has to go virtual. And so actually, we usually have about 75 students from around the world who come. And we expect it might even be somewhat larger this year, but we're going to have a big physics component to that, and strongly encourage people who are interested to apply to the summer school. And we hope probably by next week we'll have information about exactly what we're planning with that. But that's hopefully will be a good place to really learn about this stuff in detail. People have been asking about books to read to learn about this stuff. A book that I think is really pretty good, but might have a bizarrely tiny audience is Roger Penrose's book about the road to reality, which is kind of a big collection. I find it really quite amusing that Roger can go from explaining what complex numbers are to some absolutely bizarre thing about twistor space within half a page. So it's not completely clear that that's it's maybe a little bit like this live stream. We're jumping between things that are fairly elementary and things that are really quite advanced. But I think that book is potentially a pretty good summary of lots of kinds of relevant mathematics and physics, although it may have some incomprehensibility problems. I have to recommend my own new kind of science book, which has particularly the notes at the back of the book have a lot of background material that's highly relevant to what we're talking about here. And I actually am always quite pleased when I look at it that it's at least I understand it again. That's a good start. Okay, Math Boss X. Okay, seems pretty clear that quantum computers will be helpful for computational problems that are MP hard, like integer programming. But would there be any benefit for numerically solving partial differential equations or finite dimensional nonlinear programs? Could we solve Navier-Stokes faster with a quantum computer than a classical computer? Oh, good question. The big frontier of that type of work these days with partial differential equations and so on is using neural net methods. Essentially the idea there, the meta idea is this, back in the day, one was approximating functions with power series or with splines or with things like this. Neural nets are essentially a new way to approximate functions using much fancier kinds of approximation black boxes and ways to do those fittings by doing neural net training. And certainly, what we've seen in things like solving differential equations, even solving PDEs, you can do pretty well with neural nets. You can say, what are the eigenmodes of this particular partial differential equation in this boundary, in this region. You can get a pretty good estimate with neural nets. Exactly what the interface between those estimates and sort of cleaning them up and making them more precise is, I'm not quite sure. but that seems to be a good frontier. In terms of quantum computers, I mean, let's be clear. It's not clear that quantum computers, in a sense, work. I mean, it's not clear that there's something magic that you can do with them. What is undoubtedly the case is that using more physics in the construction of computers will let computers be constructed better. And I mean, our current approach to constructing computers of, lithography, silicon, et cetera, is, we're not doing optical computing. We're not doing all kinds of things which are essentially making more use of the physics. We have a very stylized way of leveraging physics in existing computers. And I think that, often quantum computing seems to be almost interchangeably used with sort of more physically based computers, whether they're optical or whatever else. Whether there is something magical about the quantum aspect, well, that's part of what we're talking about here, is whether, when we deal with these maximum entanglement speeds and so on, when we're a little bit more honest about measurement, measurement has been off on the side in quantum mechanics forever, for 100 years, basically. The, measurement was always an add-on to quantum mechanics. There's the quantum evolution, which is, works according to these linear operators and so on. And then, now we do a measurement. And that measurement was always a separate thing. I think one of the things that's happening in our models, which I think is really quite interesting, is that and by the way, in the traditional way of thinking about this, measurement is a one-shot thing typically. You have a quantum process, you let it evolve, then you measure it. The idea of measurement in bulk is a different idea. And for example, the quantum Zeno effect is a result of multiple measurement, of sort of at the beginning of measurement in bulk. But I think one of the things that we should see is with our models is a possibility of formulating essentially measurement in bulk. And I think that's going to be important in understanding the effectiveness of quantum computing, of the types of approaches that people have to quantum computing.
By the way, sorry, I just wanted to add that even independently of what we're doing in the physics project, I'm not particularly optimistic about the use of quantum computers for solving nonlinear systems of partial differential equations like Navier-Stokes, because for the reasons as we've been talking about, quantum computers are fundamentally linear objects. They're based on linear transformations, and all of the kind of the speedups that you see in those areas are based on the theoretical speedups you get from solving linear systems of equations. So there are things like the HHL algorithm, which give you, I think, they allow you to solve a system of n linear equations on the order of log n times the condition number squared quantum gate, which is a significant speed up over the classical algorithm, and that lets you do kind of faster numerical solutions using finite difference methods for linear systems of partial differential equations, where you basically have a polynomial number of gates on order 1 over epsilon for some error term epsilon. But for nonlinear systems, it's much less clear that quantum computers can offer, even in principle, any significant speed up. And I think that's a result that's independent of anything we might discover here.
Well, let me make another comment about Navier-Stokes. So Navier-Stokes, I don't know who's watching this, but I mean, in Navier-Stokes are the standard partial differential equations for fluid flow. And one of the things I've long believed is that the Navier-Stokes equations support universal computation. That is, that there exists a configuration that you can set up in a fluid, like water or something, where just watching the evolution of the fluid will perform an arbitrary computation. Once that's possible, you've already know that there's computational irreducibility in the behavior of Navier-Stokes equations, and therefore there will be a limit on the amount of speed up that you can have in figuring out what's going to happen in Navier-Stokes. I mean, there's for example, the Navier-Stokes equations, even, for example, if you look at vortices in fluids, you can ask, what are the interactions of vortices in fluids? A little bit like the n-body problem in gravitation. They can be very complicated. And, there's a question. If you have this configuration of vortices, could you make a Turing machine out of those? I bet the answer is yes. Somebody should go out and prove that, because that would be a very interesting result, to be able to show that there is universal computation in Navier-Stokes. The reason it's been comparatively hard is the Navier-Stokes equations are continuous equations. Turing machines and things like that are discrete things. Making those two things match is really hard. One of the things it's sort of one of these bounty problems is the existence and uniqueness of Navier-Stokes, which is kind of the fact you have to worry about that. When you have a Turing machine, for example, or a cellular automaton, and you say, there's no question of existence and uniqueness of solutions. The thing, you start from some initial condition, you run it, it just goes chunk, 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 and it produces an output. But when you have a partial differential equation where you're looking at sort of an arbitrarily fine differences in space and time, there is a question of, is there uniqueness and existence of solutions? For example, it could be the case that the Navier-Stokes equations, you start them off from some reasonable configuration of the fluid, and over time, the thing produces a shock wave, and that shock wave has a singularity, and that singularity is something where there's sort of an infinite density or something, where you know that the Navier-Stokes equations can't be valid because it's a derivative and you can't sort of go through that infinite shock in the derivative. Now you might say, how could that possibly happen with tame differential equations? Well, meet the Einstein equations, where that's sort of a generic problem, and where this question, and Jonathan might want to comment on this, but where this question of smooth initial conditions leading to unsmooth output is the name of the game in the Einstein equations, because that's what leads to things like black hole formation. We know for the Einstein equations that there are certain singularity theorems that have been proved. We don't have similar theorems for the Navier-Stokes equations, I believe. I mean, maybe you can just say, just for people who are interested, of the singularity theorems for general relativity.
Yes, right. So the classic one of these Penrose-Hawking singularity theorems, which effectively states something that, so from a physical point of view, it's relatively kind of obvious that if you compress enough matter or enough mass energy into a sufficiently small region of space, eventually it's forced to collapse down to a singularity. And the reason for that is effectively, if you have sufficient energy momentum density in that region of space, for it to remain static and uncollapsing would require the surface of that region to effectively become superluminal with respect to the sort of gravitational reference frame. And so basically, in order to prevent this structure from violating effectively what is locally basically just a special relativity, it has to be continually collapsing. And the limiting case of that continual collapse is the singularity point. The difficult part of the singularity theorems is actually proving that there's a formulation of this in terms of future inextendable curves and maximal Cauchy developments on Lorentzian manifolds, which is much more obscure. But the kind of the fundamental physical idea is actually quite easy. It's relatively obvious when you think about it like that.
Right, but I mean, the corresponding thing for fluid dynamics is not so clear, because the Cauchy development of fluid dynamics is non-trivial, and one really doesn't know what it might be, and one doesn't know, the wildness. In some ways, the fluid equations might even be wilder than the equations for gravity. We don't completely know their structure, but I mean, so the question here is really what is the computational complexity of solving the Navier-Stokes equations? And I think the answer I'm saying is, I think it may be extremely high. That is, it may be that it is full of computational irreducibility. And by the way, here's another point to make. In fluid mechanics, there is this phenomenon of fluid turbulence, not very well understood, where a sufficiently rapidly flowing fluid will generically show apparently random behavior. That, I think, is kind of computational irreducibility right in your face, so to speak. And does it matter? Well, half the drag on a typical airplane is a result of turbulent flow. So it does matter in some sense, and to know more regularities in turbulent flow, that is, to know more pockets of reducibility in turbulent flow, will be of high interest in figuring out how to make lower drag and how to make better heat exchangers and all kinds of different sorts of things. So, but it's not something where there's been great progress on, and I don't think. I kind of agree with Jonathan that I'm not holding out, these sort of physically based computers that one might call by the sort of brand name of quantum computers. I'm not sure that they will necessarily be at their best in studying things like Navier-Stokes. Okay, there's a question here from William Yam. What is not computable? Well, I mean, the very simple answer to that is, if you've got a Turing machine, a universal Turing machine, and you're asking, what will that thing do after an infinite time? Will it ever halt, even after an infinite time? There will not be necessarily a finite way to answer that question. Now, you can always say, but I could imagine building. In fact, Alan Turing had this idea of oracles for Turing machines. Imagine building an oracle which just tells you the answer to the question of what will the Turing machine do after an infinite time. Well, you can imagine that in modern times, those things are usually called hypercomputers. And one of the fundamental claims of our model of physics is you can't build a hypercomputer in our universe. And so that form of thing will forever be uncomputable. That question of what is the infinite time behavior of some universal Turing machine, you might be lucky and you might find one where there's a very simple answer, but in general, that will be something that you can't compute. Might our tools be of use in other hypergraph-heavy fields like VLSI design? I know less about VLSI design than I probably should. I'm aware of, I did not know that, I'm certainly aware of use of graph theory methods in VLSI design. I mean, I think as I understand it, the primary problem of VLSI design is satisfying design constraints. And if you've got trying to make a circuit of this kind, what's the sort of optimal circuit satisfying certain constraints of not having stray, I don't know, crosstalk between wires or capacitance or whatever? I don't know the answer to that. It's a reasonable question, and I just don't know the answer. Sorry. Anybody want to? Does Max perhaps have an answer to this? Or anybody? VLSI design. Anybody? Wrong team for that. There are people. Our director of algorithm R&D would know something about that, but nobody here does. Sorry. Okay. Could you copy parts of one graph and paste, I think, another graph together to run an experiment on it? Or would outside editing invalidate the whole structure? Okay, that's an interesting question. One of the really tricky things about working on this project is you don't get to do isolated experiments very well. Whenever we've tried to say, let's just isolate one effect, let's have everything else be ordinary, but then let's just have this one effect, like studying motion or something. It's difficult to do. And this question about copy pasting graphs, often that blows up in one's face, in my experience. Now, there probably are some sort of, I don't know, patching conditions that you could start to apply about being able to edit graphs. I don't think we know what those are. I think it would be an interesting thing to investigate. All right, a nice practical question from Scott Smith here. He's a C++ developer, and are there opportunities for C++ developers to contribute? I think the answer is yes. And this finally is something where Max can contribute, because Max has built a bunch of low-level code for doing optimized evolution of our models. And maybe, Max, you want to say something about what there is there?
Yeah, basically, so our implementation of Wolfram model, which is in set replace package, it consists of two parts. There's most code is Wolfram language code, but the core function, the core functions that run the simulation are in C++. And actually, if you go to our repository on GitHub, which I can show right now. So if you go to lib set replace directory, that's where C++ code is. And one thing we actually need here is to parallelize it, because right now it runs in single thread, which is, it's sufficient for our purposes so far, but eventually we are going to want to run very large simulations for many steps, and we need to parallelize it for that. So the first step will be useful to just parallelize it once on a CPU, but eventually GPU parallelization will be useful as well.
Can you say something about what's involved in parallelizing it? I mean, in a sense, this model should be, infinitely parallelizable, but I think there are probably.
Yes. So, yeah, the universe should really be distributed algorithm. That makes sense. So the only reason it's not trivial to parallelize right now is because the way we create new vertices. So we essentially have a, well, the vertex names are global right now. So each time we create new vertex, we just increase the counter, which prevents us from parallelizing it. So essentially,
why aren't we using UUIDs?
Okay, so
why don't we just use UUIDs?
Okay, so here's the problem. If we want to keep specific evolution order, then it's hard to parallelize it. If we don't care about evolution order at all, and I don't mean just uniformly random evolution, I mean just some arbitrary evolution, or we emulate the entire multi-way system, then it's much easier to parallelize.
Right. I think maybe we should make it clear to people that the most efficient code we have is single branch evolution. That is, we're picking a particular updating order, a particular order of applying updates, and we can then sort of blast through that at high speed. And that's what your code is doing. There's separate code, which is for multi-way evolution, where we're actually keeping track of the whole multi-way system, but the multi-way system gets quite big quite quickly. And I think one thing we don't have is highly optimized code for dealing with the multi-way case. What you're talking about is the sort of single thread of time, effectively, single thread of history case. And then the question is, what exactly is the updating order that we're using? And what you're saying is you need global communication to guarantee a particular sort of easily explainable updating order. But I think there are many purposes for which just any reasonable updating order is going to be useful, because we're not seeing the whole multi-way system anyway. And one of the questions is, what is the typical behavior? Okay, so one feature is it does seem to be the case that for any of these systems that's has any degree of computational irreducibility as generating intrinsic randomness, the statistical properties of the behavior after a large number of steps are largely independent of which particular branch of the multi-way system you pick. There are many detailed effects that depend on different branches of the multi-way system and the interaction between branches. But if you just want sort of the bulk question of, is there a black hole forming in the space or something, you will likely be able to get that by following just any of many possible updating orders. And so that makes it less necessary. I mean, I think the thing you're saying is that the difficulty in parallelization is maintaining global information to maintain a particular explainable updating order. Is that a fair statement?
He got distracted in the question. Can you repeat the last?
Okay, I'm going to assume I was talking about the need for global communication as a way to maintain a particular sort of explainable updating order. If you say it's going to be a random updating order, it's easy to make it distributed. Is that a correct statement?
Yes. So actually, someone was just saying we could use a global atomic integer across all the threads. So that doesn't quite work because we create a lot of vertices all the time. So if you have a essentially global index, that's just going to slow down everything too much.
How do you do a global index? Don't you have to have locking to do a global index?
Well, yeah, we will have locking, which would happen at every update event.
Yeah, so that ruins the parallelism.
Pretty much, yeah. But one thing we can do, however, is that every time we create a new vertex, we can name it according to the hash of its inputs. And this way, the vertex names would be deterministic, but they also don't require any global communication.
So we were looking at that like a month or two ago, of basically doing the Git style naming of every vertex. And that, where essentially within every vertex, it's kind of a rather poetic thing. Within every vertex is its whole history, is a hash of its whole history in the universe, so to speak. But that causes some problem, right? That leads to.
Well, it causes some problem if you only use ancestor vertex names. If you also name the edges and you include the edges in the hash, then you get the same evolution as we have now in Wolfram model.
So wait a minute. So you can say, so what you're saying is, if you progressively hash, so it's like a blockchain, basically, you're basically hashing at every stage, you generate new vertices, and you have a hash that depends on the whole history of those vertices. Is that right?
Yeah.
Then you say that will work. Well, so that seems like a good idea. I mean, it's sort of a blockchain hypergraph or something. Is that right? I mean, it's effectively every vertex hash is the back. It's a multi-way. What it is, it's instead of being a blockchain, it's a block multi-way system in some sense, or whatever you'd call that. I mean, it's a thing where every thread of the multi-way system has a succession of hashes on it. Is that right?
Yeah. So speaking of multi-way system, so one of the issues we have with a multi-way system function is that it operates on the entire states. So every time it applies an evolution event, it takes the entire state of the system, and well, it essentially at every vertex in multi-way system, it keeps the entire state, which means, as states get large and you have a lot of the multi-way system, it will get pretty slow. So one thing we will probably do pretty soon is, instead of doing this global multi-way system, we are going to branch locally, meaning that even if some region of the state, we can apply a rule in different ways, we are not going to copy the entire state. We're just going to keep track of all the edges that get produced in that region. And then once we have all those edges, we can then combine them into global state at the end.
So this is the kind of a Git-like story again of kind of trying to have patches. In other words, instead of saying we have this global state of the multi-way system, these global branches in the multi-way system, each branch is a collection of patches in some sense. Is that right?
Yeah.
Yeah, I mean, look, these are all things, people on the stream here who are asking about contributing, these are all things that'd be fantastic to contribute to the GitHub repository and so on.
This local multi-way system, its implementation will be in C++ because it's modification of our single-threaded evolution. So that's definitely something C++ developer can contribute to.
By the way, we should mention that this distinction between local and global multi-way systems is effectively the same as the distinction Stephen was talking about earlier about isolatable versus non-isolatable experiments. The question of when it becomes possible to basically break off your updating events and consider them as purely local versus considering them as embedded in the whole global state is kind of a version of this question of, is it possible to perform an isolated experiment?
Well, but I mean, the difficulty here, obviously, is the patches for these. I mean, this is also the question of how well it's going to work to make a local multi-way system is a question of the structure of branch Hilbert space. Because the question of whether you can have separate patches and essentially separate regions of branch Hilbert space which can be independently evolved is related to the whole sort of geometry of branch Hilbert space. So I mean, the physics is going to enter into how well this works. Let's see, there's a question here. Let's see, don't use interlocked functions to operate on atomics. I don't know what that means. I'm hoping Max knows what that means. Max, interlocked functions.
Not immediately.
What's that?
Not immediately.
Okay, fair enough. All right, well, good. I feel better then. We'll figure that out. Let's see. Let's look at a few more of these practical questions, and we'll go back to talk about some more of these theoretical questions. Somebody's asking which universe you have on the screen, Max, behind you. Which universe are you in right now? He's in the
oh, that's 1-2 goes to 1-3, 1-3, 3-2.
Okay. It is a universe where we can guarantee that Max is in a universe in reality different from the universe that he has behind him. That universe he has behind him is not a promising universe as a candidate for our real physical universe.
Yeah, that's a pure nasty one. Actually, I can comment a bit with the previous question. So one problem with parallelizing a specific evolution order is that evolution, depending on the evolution order, we might get different dependencies between events. So it's possible to have evolution order in which we actually have to apply everything sequentially. For example, if we always take the most recently created edges for the new event, then it's very likely it's going to be sequential. And in order to know where the evolution is going to be sequential or not, we need to know which events have been already applied. Which means if you're going to parallelize it, like one thread would have to know results from another thread to determine whether it should pick some other edges or whether it should pick the results of a different thread.
What's the relationship between the causal graph that comes out in the physics and the question of what can be parallelized? Because parallelization is essentially ultimately, a foliation of time is a total ordering applied to the partial order defined by the causal graph. What you're doing is you want to separate, it's some graph theoretic problem on the causal graph, isn't it? What you can parallelize.
Yes, so we have to parallelize, different branches of the causal graph can be parallelized, but we cannot evaluate in parallel essentially time-like events which have causal connections between them.
Right.
So if the causal graph is a line, for instance, you can't parallelize it at all.
Right, but so what you're saying is you can parallelize space-like separated events, but as soon as there's time-like
and branch-like separated events.
Right, in the multi-way graph, right? So
yes.
So in a sense, there's a physics problem. I mean, this is where the physics interacts with the distributed computing, so to speak, is that what you're doing then, the question then, okay, so what's the physics question of is it parallelizable? So in other words, that's a question of, is there a space-like patch? Is there a separated space-like region that will not have, it's a light cone story. It's the story of what, because any time that you have your two light cones intersecting, you will have to do what are they called? Oh gosh, what are they called in theory of distributed computing? One of those locking events.
Critical section problem?
What's that?
Critical section problem?
No, I'm thinking of just the interlock, the synchronization, basically.
Right.
Once the light cones intersect, you have to do synchronization. But what you get to do is two non-intersecting light cones, you get to evolve separately. And so I guess what I'm asking is, what's the physics analog of making the statement? I mean, what that basically means is that these are, you can evolve separately, causally separated parts of the universe. Those can be assigned to different processes.
But that's what I was trying to say about this notion of, can you do an isolated experiment? Because basically what's going to happen is, if your multi-way causal graph has so many kind of causal connections between different multi-way evolution branches that there's no consistent foliation that doesn't have a bunch of these overlaps, then that's a very unparallelizable situation. That's also exactly the situation where you basically can't just break off a piece of the hypergraph and do an isolated experiment without it affecting a whole bunch of other things. So okay. I think basically this question of when it's possible to do these kind of parallelizations will correspond to the question of when it's possible to do isolated experiments.
Well, okay, so there's another point that you're making there, which is the foliations that you choose. So the question is there a foliation that corresponds to a doable parallel computation? So it's similar to when you're doing search, right? It's there's depth first searches, there's breadth first searches, and so on. And that's very much what we're talking about here, right? You could do a depth first traverse through this causal graph, and that will be one kind of sequence of operations that you do, or you can do various kinds of breadth first things that correspond to different foliations. And I think what you're asking for is something where there is I'm a little bit, okay, a foliation involves a single slice, that you're defining a simultaneity surface across the whole of the universe. And I think what you're asking for in this parallel computing case is a patchwork of simultaneity surfaces that somehow fit together at the edges. And maybe there's an understanding of that in some area of parallel computing, distributed computing. I think, back in the day, I don't know how much of this there's, in modern times, I think a lot of distributed computing has to do with computing that is not, not in arrays. I mean, there used to be these things, systolic arrays or massively, cellular automaton-like machines and so on, where there was much more of a spatial character to the understanding of parallelism. I think these days that's probably not as much a thing. But in order to, in our case, where we actually have a physics underneath and where we have this notion of meaningful space-like separation, that probably is more important again. And there's probably some theory of how you can, what the maximum degree of parallelization is and how that relates to the physics. Somebody is making the comment here, I think that's Tally, making the comment here that the good news is that the vacuum parts of the graph should be nicely compressible. I don't think so. The vacuum is a big, complicated mess. I mean, in our current estimate, one part, the matter in the universe is only 1 part in 10 to the 120 of all the computation that's going on. In other words, all but 1 part in 10 to the 120 is about the maintenance of space. That's about maintaining the vacuum. So once you've maintained the vacuum, 10 to the minus 121, that smaller piece is everything we know in the universe. Everything we care about in the universe is just riding on top of the maintenance of the vacuum. So the vacuum is already a very complicated thing. And the question of the compressibility of the vacuum, that is an interesting question. That is an interesting question. How much of the operation of the vacuum, how much of the irreducibility in the operation of the vacuum is important? And it's a really good question. I actually have no idea what the answer to that is. I mean, I think that, okay, so it could be the case that the vacuum can be thought of in bulk. Okay, reasonable question. Is the vacuum kind of like a bulk material where you can really compress it and just say, these are the attributes of the vacuum, it's going to be the same everywhere, we can just jump ahead and work it out? My guess is it's going to eventually matter what happens in the vacuum. Let me give you an analogy. I think it's actually analogous to the fluid turbulence problem. The question is, in turbulent fluids, does it matter what the individual molecules are doing? Is there an amplification of the effects of the individual molecules that can affect the large-scale turbulent flow or not? And I think it'll be the same type of question for the structure of the vacuum. It would be my guess, at least.
By the way, this is basically the question of what is the entropy of empty space, right?
Yes. That is the question.
This is not entirely unrelated to something which maybe we'll get to address today, or possibly we should address in a different live stream, which is this ER equals EPR conjecture, which potentially gives one a way of computing that quantity, because it says that effectively empty space has a certain entropy associated with it, which is related to an entanglement entropy. But basically, the within the formalism of the ER equals EPR conjecture, empty space is made up of this very large lattice of of quantum entanglements, and somehow the geometry of the space emerges as a consequence of the individual entanglement entropies, and it gives you a way to compute the kind of what the entanglement entropy of the underlying space would be, which I suspect is what ended up being the case here.
Well, why can't we just go right ahead and compute the entropy of the vacuum? I mean, we know what our computation of entropy is. We have an ensemble. It's the branches of the multi-way system. We don't have a normal statistical physics. The ensemble is a fake. I mean, that is that an actual statistical physics system in classical statistical physics has a particular path of evolution, and we have to assume an ergodic hypothesis to sort of map that into what would happen in an ensemble of all possible initial conditions. But in the case of the multi-way graph, we actually have an ensemble right there. So we should be able to compute essentially some kind of partition function that gives us, so let's think how to do that. So, I mean, what that's asking is, summed over the branches of the multi-way system, we would have some, we have to ask the question, essentially the entropy is just this question. So it has a little bit of technical complexity to it, but if we imagine, okay, so if the multi-way system generated all possible hypergraphs of a given size, it would have maximal entropy. So the Jonathan is pondering something here, I can tell. So I think that's the way to think about it. Is does the multi-way system sample all possible hypergraphs, or does it sample only some subset of possible hypergraphs? Now, unfortunately, the space of all possible hypergraphs is kind of a mess. I mean, unlike something like the space of possible configurations of a cellular automaton, which is some very easy combinatorial thing to work out, the space of all possible hypergraphs is more complicated. But so I would claim that we can compute an entropy, and the entropy is just equal to the fraction of the number of possible hypergraphs, the logarithmic fraction of the number of possible hypergraphs that you actually see. And in other words, so therefore we have a, and what do we think that quantity is? It's related to our capital Xi quantity. Oh, that's bizarre. You know, the usual symbol for the grand canonical partition function is a capital Xi. And it would be quite shocking if by pure chance we ended up with the same symbol for our multi-way, number of states in the multi-way system as the grand canonical partition function.
But that's not in any way surprising, right? Because Xi is some kind of measure of global branchial extent, and
yes.
Our current best sort of mathematical formalism indicates that probably the natural distance metric on a branch-like hypersurface is sort of entropy, is the Fubini-Studi metric, which you can use as a direct proxy to entanglement entropy. So the fact that entropy would be related to this notion of branchial extent is entirely natural, I think.
Yeah, right. But I mean, it's also clear that there has to be right because it is a question, because we actually have an ensemble. Our multi-way system is an ensemble. It is a physical instantiation of the ensemble. So just walk me through the ER equals EPR story with respect to, so what we're saying here is we should be able to compute the entropy of empty space, basically. We should be able to compute the entropy of the vacuum by simply working out the branchiness of our multi-way graph. And in particular, what is the implication of, what's the implication of causal invariance for that? So that causal invariance, the maximal entropy, I believe, is not achievable if you have causal invariance.
Yes, that's exactly, because causal invariance places definite upper bounds on how large Xi can be, because otherwise you just have branch pairs that have no hope of ever resolving.
Right. So that would mean that the fact that the vacuum, this is saying there's a constraint on the vacuum. The vacuum cannot be all possible hypergraphs. The vacuum has to be constrained, and that constraint will depend on the resolution time for the for the causal invariance of the branch pairs. And I wonder whether there's a bound. How does it relate to the structure? How does it relate to the distance, the size of a geodesic ball in branchial space? So what is there's two different forms of entropy here. One would be the entropy that's associated with the whole of branchial space. That is the number of possible hypergraphs in the whole of branchial space. The other is in a particular region of branchial space, we're looking at the growth rate of the geodesic ball in that region of branchial space. And that will give you and so that, in a sense, we can think of that volume. Actually, maybe you've been saying this for ages and I just haven't understood, because you've been talking about entanglement entropies and I just don't know that literature. So what you're basically saying is the volume of branchial space is related to the entanglement entropy.
Yes, exactly. Or to put it another way, when you release one of these geodesic bundles, that's this notion of an entanglement cone in branchial space. And so the question is, obviously in ordinary space-time, you talk about when you release a light cone, that allows you to deduce sort of conformally invariant features of the space-time, and in particular, it allows you to define a space-time metric. And that natural space-time metric is this sort of generalized Minkowski metric in a pseudo-Riemannian manifold. Then the question is, what's the sort of analogous notion in branchial space when you have one of these entanglement cones? And it seems like one of the most natural ways of formulating it is in terms of this Fubini-Studi metric tensor instead of the space-time metric tensor. And so yes, exactly. But one of the implications of that would be that the natural way of quantifying kind of extent in a branch-like hypersurface is in terms of entropy, in terms of entanglement entropy.
No, well, I now finally understand that. I think you've been saying that for at least a couple of months.
It's good that we figured this out now. Yeah.
Right. But I mean, so what you're saying is, because the different branches of the multi-way system can correspond to different pieces of the ensemble, that is directly computing an entropy. And
exactly.
And so now I'm motivated to understand this Fubini-Studi metric, which I've never been suitably motivated to understand before, and that which you claim is related to Fisher information, which is
So the real part is related to the Fisher information metric. Well, it's related to the quantum Burroughs metric, which is the sort of quantum analog of the Fisher information distance. So at some level, the whole thing can be viewed as being a sort of measure of algorithmic information distance on projective Hilbert space.
Let me unpack that. That's all right. We should go back to some of these questions on the live stream. That got rather technical. Sorry, guys. Okay. So Tali is making some other points about systolic arrays is still going strong. Okay. They're used in neural net accelerators. That's right. That's right. I did know that. Yes, I did know that. Yeah, because they accomplish matrix multiplication efficiently within minimum of on-chip communication. Right. So, right, because they're trying to have data. They're sort of a systolic array, by the way, is very much like our causal graph. I mean, our causal graph is an instantiation of the data flow of a systolic array. I think let's see. Someone's asking here, what tensor did Jonathan suggest? I think
I just sent back a reply. I should have done via one of our moderators.
Okay, fine.
But it's the Fubini-Studi metric tensor is what I was talking about.
You want to say something? Just because I'm now motivated to. You've been talking about this for ages, and I haven't been that motivated to understand it. But so now I'm more motivated to understand it. Can you give some intuition for what that metric actually is?
Yeah. Okay. Sure. So, sorry, stop my video. Yeah. So it's in ordinary Hilbert space, right? The standard Hilbert metric is a completely flat metric, so it's kind of completely uninteresting from the point of view of doing sort of differential geometry. But in projective Hilbert spaces, where
maybe you should say something about just for our general education of people, for Hilbert space, talking about metrics in Hilbert spaces and complex numbers.
Okay. Yeah. Sure. So a Hilbert space is, I mean, in the most general mathematical sense, it is a notion of space in which you can compute norms and therefore distances. So, most of the ordinary kind of geometrical spaces you can think of, at least the ones that are linear and don't have curvature, you can think of as being Hilbert spaces. But the place where they get interesting is because they naturally generalize to have coordinates that aren't just real numbers, but are actually complex numbers. And also, moreover, they generalize from sort of finite dimensions to infinite dimensions in a fairly natural way. So generally, from the point of view of quantum mechanics, we're usually interested in the infinite dimensional complex Hilbert spaces. But even then, their distance metric is basically just the Pythagorean distance between complex vectors. And so it's not, as I say, it's not particularly interesting from the point of view of differential geometry. But it turns out you can get this additional structure if you basically have projective points. If you allow for the existence of points at infinity, then you get this thing called a projective Hilbert space, which can actually have a non-trivial geometry. It can have curvature on it, just like things like space-time can have curvature. Natural way of quantifying that curvature, then that's really interesting, because from the point of view of quantum mechanics, the Fubini-Studi metric tensor is a way of computing what's called the Burr's metric, the Burr's distance, Burr's angle between pure quantum states. Actually, there's a more general formulation in terms of mixed quantum states. And so that's a way of quantifying entanglement distance between quantum states. And the real
What is the actual metric? What is the computation? So you've got a quantum state which is represented by a state vector, and then what is the actual metric there?
So assuming you have, it gets a bit more complicated for mixed states, but if you just have pure states, it's an arc cos of a square root of a bunch of projections of one state onto the other. I forget the exact order, but it's actually relatively simple to compute, and that gives you this quantum Burr's angle. And then it turns out that the real part of the quantum Burr's metric is related up to a factor of 4 to this Fisher information metric. And the exciting thing about that.
What's the physics of the Burr's metric?
So this gives you a way of effectively, okay. It's one way of evaluating distance. So there are many ways of evaluating distances between states in of quantum states in Hilbert spaces. There are things like trace distances, fidelity distances, things like this.
It's like vectors, any old vector. I mean, there's cosine dissimilarity or whatever is some random thing that sounds a bit like what you're talking about actually, which is just some random way of assessing the distance between two vectors. Right.
Yes, exactly. But the Burroughs metric is a naturally information theoretic way of quantifying that state distance, which is a result of the fact that it's related to this Fisher information. So basically, you can think of it as being some kind of measure of how many measurement operations you would have to perform in order to be able to distinguish those two states. So it's a measurement constrained way of expressing distinguishability between quantum states. And as I say, up to a factor of 4, its real part is related to this algorithmic information distance. And that's interesting because our natural distance metric on branch-like hypersurfaces is also an algorithmic information distance. Again, we can go into more detail about that if people are interested. But that gives us a kind of tangible mathematical connection between the geometry of a branch-like hypersurface and this Fubini-Studi metric tensor.
Okay, I mean, but I want to come back to at some point this entropy of the vacuum. What is the? I mean, so if we knew the entropy of the vacuum, you know, back in the day, I had this paper called Properties of the Vacuum, Mechanical Properties of the Vacuum. Okay, which to my great amusement, I wrote it in 1981, so a long time ago, and to my amusement, it actually became a one of the features of that became a scheme for interstellar propulsion that people studied. Because what that paper was about was this thing called the Casimir effect in quantum field theory, where you have a box and you change the size of the box, and there's actually a different energy that associated with the vacuum as you change the size of the box. So I never thought about this, but the question is, what are the gas laws for a vacuum? If the vacuum can be thought of as having an entropy, what does it mean? You know, if you have a box full of vacuum, and you can then start applying thermodynamic thinking. I mean, that's somewhat related to the old Bekenstein kind of approach to thinking about black holes and so on. But I'm curious, but understanding that in terms of the quantum, vacuum, I had not really thought about. Is that a thing that people understand as sort of pieces of vacuum in boxes and understanding entropy computations for those? Or do we have to figure that out?
No, that's certainly something people have been computing in the context of this ER equals EPR idea. That basically that there's a natural, if you have a kind of Bekenstein-Hawking type. Okay, one way of formulating the ER equals EPR conjecture, sort of from a mathematical standpoint, is to basically say that Bekenstein-Hawking entropy is the same as entanglement entropy at some level. And so if you have a way of computing if you have a region of vacuum and you have a way of computing in a Bekensteinian way what its entropy would be, there's an immediate way you can kind of reformulate that in terms of entanglement distances between states and things like this. This is certainly something people have investigated.
Right. Let's see. It sounds like we're at our stopping time here. Let's just see what other questions and comments. Yes, Tally was commenting here that there are pockets of compressible behavior, for example, in the Golly cellular automaton accelerator for Game of Life. There's the ability to do, yeah, that's interesting. Okay, so Game of Life, for example, is a very kind of airy cellular automaton. Not a lot happens. There's just a few places where there's activity. My guess is that in the case of the physical universe, that it's just full of activity, and that the pieces of things that correspond to identifiable particles are essentially pieces of topologically stable structure, where I generalize the term topology, and that it won't be possible to do that same kind of compression, although there might be some statistical compression that could be done. There's some lossy statistical compression of the behavior of the vacuum that could be done, and that's an interesting idea. Let's see. Okay, just a minute. We got a question here from CGOM. You guys are talking about black holes and creating quantum computers. Serious question. What are the chances that humans, in an attempt to achieve something like this, create a black hole that consumes the planet and causes widespread devastation? Yeah, it's a good question, particularly in these times of what happens if you make the wrong RNA sequence and it and it starts taking over the planet. Yeah, that's a Well, that's an interesting question. I mean, we're all merely passengers in the evolution of the universe, and the question of whether our particular, whether there could be in our future light cone, so to speak, whether we could wind up, in some black hole, is an interesting one. I mean, I think, there was a big concern when the LHC, the Large Hadron Collider, came online. There was this. I have to say, it was not the greatest moment in public relations for physics, because basically nobody cared about the Large Hadron Collider until somebody, tried to get an injunction to prevent it being switched on the grounds that it could create a black hole that would destroy the world. And that was the only thing that seemed to get any kind of public interest in the Large Hadron Collider. I mean, the parameters are very far away in terms of what it would take to, the creation of a causal event horizon for a black hole, from what we know, is just far, far away from anything human achievable. An interesting question, I suppose, is, well, we're talking about branchial black holes. We're claiming that qubits are a story of branchial black holes, but you don't have to worry. A branchial black hole, I don't think, and I'm trying to get Jonathan's attention here because this might be critical to the, I don't think branchial black holes can, what is the, there are different kinds of black holes. There are branchial black holes, there are disconnected regions of branchial space, there are causal disconnections, and there are actual disconnections in the hypergraph. So causal disconnection is the normal black hole story. Disconnections in the hypergraph are something different and new that I don't know what that corresponds to. I don't know what that would, in general relativity, I don't know what on earth that corresponds to. I mean, it's not like you have coordinate patches. You have just a disconnected lump of coordinates. I don't know what is there an analog of that in general relativity?
Probably the closest thing that exists are these sort of bubble universes that appear in certain kinds of eternal inflation models. So in certain models of cosmology where you have an inflaton field and it doesn't switch off uniformly everywhere, you basically get sort of different patches of space that get sort of inflated at different times. And so each of those behaves like a completely causally disconnected universe, in effect. That's probably, and there's a way you can formulate them as in terms of sort of completely disjoint space-like hypersurfaces. That's probably the closest analog that exists in conventional general relativity.
The reason that won't occur in the conventional view is that in the conventional view there is a background, 3+1 dimensional space, and once you have a background 3+1 dimensional space, you don't have different, coordinate patches. It's just there is this space, and it just sits there. And so you don't really have this possibility of a disconnected piece of a disconnected piece of space just isn't a notion. So I mean, that's the worst case. That's the worst form of social distancing, is to be in a disconnected piece of space that just has no possibility of reconnection with the rest of the universe. So that's kind of the ultimate bad case scenario. To be in a causally disconnected part of space, you're still branch pairs can still reach you in the causally disconnected region, which is, the analog of Hawking radiation and so on, and you're able to have communication through branchial space, basically. You can't have causal communication in physical space, but this is this idea that the entanglement horizon is outside the causal horizon. So I think you're still not completely lost there. So now in branchial space, we're talking about a separation in branchial space, which is much more benign than a separation in fact, the separation in branchial space, we're claiming you have to put, let's put it this way. What we're saying is, to maintain a black hole in causal disconnection, a black hole with causal disconnection, you have to put energy into it by throwing matter or something into the black hole to prevent it just evaporating away in Hawking radiation. You have to keep the size of it. You have to fatten up the black hole, basically. You have to keep the black hole fattened enough by feeding it enough stuff that it doesn't just evaporate away. So now, in the case of a branchial black hole, I guess it's the same kind of thing. You have to feed it enough edges in the multi-way causal graph to keep it fattened up so that it doesn't evaporate away in a bunch of branch pairs. But now the question is there a way? Okay, so this would be this is this is the moment we have to be sure we're not doing something terrible. That, can one, by trying to maintain a branchial black hole, could one end up with a causal black hole?
Well, I think it could potentially be even worse than that. If you try and maintain a sufficiently large branchial black hole that encompasses the whole of the branch-like hypersurface, basically what you've done is, at least from the point of view of that observer, you have forced the universe to terminate at a normal form, right? Because you've basically forced the multi-way evolution to halt around the state that's at the center of that singularity. So one bizarre doomsday scenario is if you try and perform a sufficiently big measurement, or otherwise to try and build a sufficiently big quantum computer, you could end up basically forcing our universe to terminate as a normal form, at least in your reference frame.
Yeah, in your reference frame, but that's not, so what does it mean? Okay, so let's just take that scenario. Let's say, if we assume that we're right about the rough order of magnitude of the maximum entanglement speed of 10 to the 5 solar masses per second, assuming that we are a giant quantum computer that spans where we're eating things at the rate of 10 to the 5 solar masses per second and so on, very big, the Goliath, quantum computer, so to speak. What does it mean to say that in that reference frame it's terminated in a normal form? That means that for that, with respect to that quantum observation frame, the experience, I don't think that's, the experience of the Goliath quantum computer would be the universe is over. Nothing more will happen.
Right, and basically the reason why that happens is, so we mentioned a couple of times this quantum Zeno effect, which is sort of our analog of time dilation in the sort of branchial space. The way that works in conventional quantum mechanics is you say, if you have two states and they're separated by an evolution over a unit interval, if you punctuate that interval by sort of instantaneous projection operations that are sort of the idealized version of measurement, as the number of times you punctuate that interval goes to infinity, the sort of the time it takes to evolve between those two states also goes to infinity. So effectively, as you try and measure something at a sort of progressively larger rate, its sort of natural rate of evolution through the Hilbert space sort of goes to zero. So one of the implications would be, so if you tried to do, as Stephen just mentioned, if you tried to build a really big quantum computer that basically swallowed kind of most of the microstates of the universe, it would be performing entanglements and it would be performing measurements at a sufficiently high rate that from the point of view of that quantum computer, there would be like no time evolution would be possible. The quantum Zeno effect would go to infinity, so it would be like you're at the it'd be like you're at the singularity of a black hole. There's no time evolution for you at that point. And so yes, so from the perspective of that sort of quantum computer, that idealized quantum computer, the universe would have seemed to have terminated.
I don't think that's right. I don't think it's right, because think about a thing falling into a black hole. To a distant observer, the thing falling into a black hole freezes time, but to the actual entity falling into the black hole, time still progresses, right?
Well, no, because if you're at a singularity, the outside, infinite time has passed in the outside universe.
Right.
Right. So what you're doing is you're evolving an infinite number of steps in the multi-way evolution graph, which I claim is the sort of analog of terminating at a. If you have an infinite multi-way evolution graph, evolving for an infinite number of steps is the analog of terminating at a normal form for a finite multi-way.
So what you're saying is, to somebody falling into a black hole, and particularly in like a Kerr black hole where you have these weird, outer event horizons and things, you can see the whole future of the universe. That is, you in your finite time, so to speak, you get to see the whole future evolution of the universe sort of flashing before your eyes, so to speak. And so in this case, what would happen is that through this giant quantum computer, it would kind of see the whole future evolution of the universe flashing before its generalized eyes. And then that would, and then it's all over, because it's seen the whole future evolution of the universe, right? It's seen every one of those little, time steps. It's already seen. So it's kind of like, it's over. Then it's stuck. Then it's at a normal form, because it already saw the whole future evolution of the universe. So what you're saying is, if you could, but that's a thing that happens only in a giant, if you can cover the whole branchial space. The question is, if you just got a little tiny qubit in a lab somewhere, in a cryostat somewhere in a lab, what does that, the maintenance of that branchial black hole for that qubit is a very modest sized black hole, so to speak, in branchial space. And the question, I guess, is that we're sort of being asked to think about here, which I think we should think about, is the kind of, is there any way that a branchial black hole, a modest-sized branchial black hole, being maintained by throwing branch pairs into it, so to speak, can turn into a causal black hole? I think
so. Yeah, I think that's going to happen in general, right?
Why?
Because cause. Okay. Actually, maybe not.
It better not be the case. Or quantum computers
I
are
take
very,
that back.
very
I take it
unsafe.
back.
I mean, if that could happen, if the maintenance of a branchial black hole could lead to a causal black hole, then we should shut down all quantum computers immediately, because the Earth is going to be consumed by a black hole in short order. So I don't think it's the case, but I think it's
the converse. I think has to be the case, though.
What's that?
I think I was getting confused. I think the converse.
The converse is the case. The converse is the case. If you have a causal black hole, then you have a branchial black hole, because that's the statement that there's an entanglement horizon associated with a causal horizon. But I think the converse is not true. What we want for a branchial black hole is an entanglement horizon, but not a causal horizon. I mean, the sort of health and safety requirements say we shouldn't have a causal horizon in our lab. All right, let's just, how do visualizations decide where vertices in the graph are placed? So we're trying to place the vertices so that the distance in the space in which we're portraying the graph more or less agrees with the distance within the graph. That is, two vertices that are adjacent in the graph are shown as nearby in physical space. And why do we want to do that? Well, we want to do that partly so that we humans can get an idea of what on earth these hypergraphs actually are doing, because otherwise you have this sort of arbitrary tangle of wool and arbitrary ball of wool, and you can't sort of figure out what the geometry of it is unless you've kind of mapped the kind of the graph theoretic distances onto the onto the kind of distances of visualization. Okay, let's just have a quick look through to the end here, and then I think we have to wrap up. Can I apply two rules at once using Wolfram model tools? Yes, the answer is yes to that. You just put them in a list. Okay. Okay, Tally is asking, have we considered imaginary time evolution, open quantum system dynamics? What does Wick rotation mean for multi-way systems? All right, let's just take that one. This was supposed to be the computation Q&A, but all right, let's talk about Wick rotation for a minute. I think that's, well, I think we've talked a little bit. So Wick rotation, for people who are not into this, is the usual usual view of space-time is that it's like Minkowski space, where distances are t squared minus x squared. But a Wick rotation says, take that t and make it an imaginary time, so that then it becomes like Euclidean space, and the distance metric is t squared plus x squared. Okay, so Wick rotation is what is done in lattice gauge theory, for example, to turn what would otherwise be a quantum field theoretic computation into a statistical mechanics computation that can be done in imaginary time. And one of the ideas we just talked about yesterday is the idea of using our kind of multi-way system or multi-way causal graph as a way to do actual non-imaginary time computations in quantum field theory, which has been something that basically I don't think there's any real methods for doing. I mean, people doing numerical path integrals, I don't think that's gone anywhere. I mean, people were doing that. I've got this a little bit of a Rip Van Winkle effect on my knowledge of particle physics, because I worked a lot on this 40 years ago, and it's back then people were trying to do numerical. In fact, I even tried to do some numerical path integral stuff, and it really didn't work at all. It was just full of weird infinities and all kinds of other problems. So this might be a way of doing numerical path integrals, which I think would be super interesting to investigate. But now, okay, Wick rotation. Let's see, what do we have to say about that? I mean, basically what that's saying in a causal graph, Wick rotation would turn the directed causal graph into an undirected graph, right? I mean, that's what it would mean to take, I mean, roughly. I think, Jonathan, you had some claim about Wick rotation a little while ago that was...
Yeah. So this is actually, this feeds into this more general claim about how the signs of coordinates work in branchial space. So if you have a space-time causal graph, right, you have to distinguish between the time-like separation and the space-like separation. So the way you do that is you impose something like a Minkowski metric, where you have two different signs, right? So the time-like separations could be negative, and the space-like separations could be positive, or the other way around, right? Depending on your metric signature. But the point is, when you then go if you then go to the multi-way causal graph, now you have three kinds of separations. You have time-like separations, space-like separations, and branch-like separations. And you can have combinations of the three. They're not actually, at least space-like and branch-like separations are not mutually exclusive. So you need to have effectively three different signs in your metric in order to be able to effectively distinguish between those three types of separations. There's a rigorous mathematical justification for this, which is called the Sylvester law of inertia, which basically tells you, for every type of separation, you need to have at least one sign change in your metric. And it's a sort of general theorem for complex matrices and things like that. But so effectively what that means is we have to have a new, we can't just rely on positive and negative numbers. We have to have a new direction for branchial coordinates. So our approach, without loss of generality, was to say, let's just use imaginary numbers, positive imaginary numbers. The nice thing about that is that immediately explains kind of why you get complex numbers for describing your projective Hilbert spaces. It also explains why you get projective Hilbert spaces and not ordinary ones, because so the projective Hilbert space is kind of, or it explains why you get this kind of, sorry, I retract my previous statement. It doesn't explain why you get projective ones instead of ordinary ones, but it does explain some sort of, it explains to an extent the projectivity, in the sense that we know that a quantum state is defined not just by a single vector, but by a whole ray. In other words, you can scale it by an arbitrary complex number and you get the same state. So there's a kind of additional degree of redundancy. It turns out, at least in this formalism, the reason why you get that redundancy is because by introducing complex numbers, you've introduced one additional degree of freedom that you didn't need. You only need three types of separation, but by allowing for both positive and negative imaginary numbers, you get an additional degree of freedom that you have to cancel off by kind of modding out by the action of the multiplicative group. And that's why you get this kind of rescaling symmetry going on. So that then introduces the question of, okay, what does a Wick rotation mean? If this is correct, what does a Wick rotation mean? Well, all it means is you're basically exchanging, it's a way of exchanging space-like separation for branch-like separation is the short answer. Because what you're essentially saying is, what if initially, instead of saying the time-like separations are negative and the space-like ones are positive, what if we said the time-like separations are imaginary and the space-like ones are positive? We could also have done that, in which case the branch-like separations would now correspond to positive numbers, and it would be effectively, you'd get the same structure, just with now the branchial and spatial coordinates exchanged. That's kind of my current intuition about how
that's interesting. We should discuss that some more. I mean, that's an interesting idea. I mean, the point with Wick rotation is, Wick rotation may cause a quantum field theory to just turn into garbage. There's no guarantee that Wick rotation will preserve, properties of a quantum field theory. And so, anyway, the different. I mean, what you're suggesting there. Okay, let me. Okay, that is interesting. So this CPT theorem that says, right? So CPT invariance is equivalent to this rotation. It's generalizing. The proper orthogonal Lorentz group is being generalized to this thing that isn't proper and isn't orthogonal, so to speak, which means that you can have the P and T symmetries, and then you have this complex number thing. So now the question is, what can you do if you allow a rotation not just in space-time but into branchial space? What does that do? In other words, there is a super version of the Poincare group, presumably, that also reflects rotations in branchial space, which would correspond to that corresponds to changing frames. So what that is a symmetry, and people have talked about these, but in some weird form that I never understood. Okay, so in quantum mechanics, so in space-time, we understand rotations, and we understand the generalization of rotations that is the Poincare group as opposed to just rotation group, or the Lorentz group instead of the rotation group, et cetera, et cetera, et cetera. Now the question is, in quantum mechanics, as we go from one quantum observation frame to another, we can think of that as being some rotation. We could think of that as being another form of sort of rotation in a space. And so the question would be, what's the analog of, in your interpretation of sort of swapping branchial space with physical space? What does that then mean? Does that suggest that there is a generalization of the Poincare group that would apply to branchial space? And if so, what on earth is that group? And what would be okay? First, one question. Insofar as the SO3 or something would be, or SO31 would be the Lie group that represents symmetries in a 3+1 dimensional space. If we've got one of your friendly projective Hilbert spaces, what is the analog of SO31 for a projective Hilbert space? What is the invariance group for a that's a simple mathematical question, which of course I don't know the answer to.
Unfortunately, I don't know the answer either, but I should do. Hang on, we can look it up. Oh, the projective symmetry group, PSG.
Oh, that's right. That's right.
Yeah.
But what is that in terms of? In terms of understanding that in terms of Lie groups and things. So that's the generalization. That would be the generalization of the Poincare group to rotations also in branchial space.
Yes, right. So this gives us the analog of Lorentz boosts and translations and rotations, but in branchial space.
What on earth is the analog of Lorentz boost?
We know intuitively what that would be, right? It would be some kind of tipping of the quantum observation frame, but how we describe that mathematically in terms of PSG, I don't yet know.
No, but the tipping of the quantum observation frame is a statement about exploring more of entanglement space over time, right? It's like the analog of motion, because the analog of motion in branchial space is moving to a different part of entanglement space over time. What is PS? What is that? What is that? We should all look this all up. But what is the thing when it from a mathematical point of view? I don't know.
So PSG2, for instance. PSU2 is just SU2 mod Z2. So it's actually SO3.
That's weird. But that must be for some weird tiny Hilbert space, not.
Yeah, right. So I think the exact algebraic results I'm seeing are only for very small, Hilbert spaces in very small numbers of dimensions.
But is it a Lie group? What is the thing? What kind of an object is it? Well, we can worry.
I don't think it's a Lie group in general, as far as I know.
I wouldn't have thought it was. I would have thought it was some more general thing. Yeah. But that's an interesting. Interesting symmetry. Okay, all right, we should wrap it up here. Let me just mention to people on this live stream, we will be doing some more live streams tomorrow. We have 2 scheduled. The first is 2:30 Eastern Time, is about quantum spin and electric charge. And I am looking forward to that because we've had a no science policy for the last month or so, as we've been trying to not have this project to have a kind of Zeno effect type feature of continuing infinitely. So we'll be actually trying to do. We did some science in this live stream here, and we'll be trying to do some more understanding those features. And if there happens to be anybody in this live stream who thinks they're an expert in relativistic angular momentum, quantum spin, those kinds of things, let us know. Then after that, at 4 o'clock Eastern Time, I'm going to be doing a fundamental theory of physics for kids, essentially an attempt to explain what we're doing for kids, kind of extending. I've been doing these Q&As, science Q&As during the pandemic. I've been doing science Q&As for kids, and I've had the frustrating experience in the last couple of weeks of questions that people ask saying, well, actually, there's this fundamental theory of physics that we've just been trying to invent, which can answer your question, but we haven't yet described what this theory is. So now I can do a version of this where I try and describe what the theory is. So those are the things coming up for tomorrow. Thanks very much for participating in this stream, and see you all another time. Okay, bye.